Greetings and welcome to another installment of Quantile. This is 26 in our basic application series. This time around, we're going to close out our practical series on hypothesis testing of a single proportion. If you want to enjoy the blow-by-blow action, and who would not, I suggest you watch this mini-series playlist in full. You can find it under the Quantile channel playlist tab. For this installment, we're going to work through one more example, then offer some concluding diagnostics. So, for example, suppose we have a soon upcoming election between two and only two candidates, candidate A and candidate B. Now, we can imagine a population of registered voters who self-report that they are very likely to vote in this upcoming election. So let's say this population is very large, say a few tens of thousands of people. So we're going to obtain survey responses from a sample of 250 individuals from within our population concerning whom they support. Now, there's actually a few ways to apply a statistical test to this scenario, but for the sake of simplicity, let's ask the research question: does a preponderance of individuals from within our population support candidate B? Well, what's a preponderance? It's any proportion greater than 1/2. So quite directly, here is our hypothesis pair. And so let's set our significance level to 1 in 20. Remember that our critical region is a space of values that contains test stat values that are unlikely if the null hypothesis is true, but may be very likely if our alternative hypothesis is true, and that defines an area under our test stat sampling distribution equal to our significance level. By the way, throughout, we're using the standard normal distribution, same distribution every time, and after you've done enough of these, you start to memorize these critical regions. Any statistician can tell you in their sleep that our critical region here is any value greater than or equal to about 1.645. And if you don't have this stuff memorized, it's not a problem. You can use a table or software or web widget to obtain the critical region here. So let's say, for example, that in our sample of 250, 133 say they support candidate B. We plug our values into our trusty function that converts our observed sample proportion into our standard normal test stat approximation and obtain a value of about 1. The value 1 is not in our critical region, and so as a consequence, we fail to reject the null hypothesis. Or said another way, we have insufficient statistical evidence to conclude that a preponderance of likely voters at large support candidate B. So we've come this far. Let's bust out with the p-value. Our p-value region is, of course, one that contains values that are rare if the null is true, and values that may be common if the alternative is true, and that contains our observed test stat. The p-value is the probability of this region, or the area of our distribution over our p-value region. By the way, another way to describe our p-value region is a region that contains values that are more likely if the alternative hypothesis is true than if the null hypothesis is true. And of course, that also contains our observed test stat. Our p-value here is about 16%. 16% is not less than or equal to 5%, our significance level, and so we fail to reject the null. We already know this. So let's do a quick diagnostic on this example here. Of course, the question we'd really like to answer is, will candidate B win the upcoming election? Applying our statistical test in the way we have been would require access to the population of all people who actually voted. This population is not only imaginary, but completely inaccessible, not until the actual election takes place. Of course, still, limiting our research question to simply whether candidate B is favored among likely voters does possess value in and of itself. This is a theme for future Quantile videos, but without intimately knowing the details, I think it would be intuitive for most to understand that nonetheless, it would be tricky to get a sample of people that represented the target population. In other words, it would be difficult to obtain a representative sample. People who would participate in our survey would likely be outspoken, and those with sufficient free time to complete our survey. This problem is called survey bias, or more broadly, sampling bias. So, before we close out this mini-series, I want us to revisit our original coin flip experiment. And here we find a much more subtle and insidious factor at play. We never described how exactly we were executing our coin flips. Consider that an illusionist loaded coin here is one that appears typical but is physically altered internally so that one side is heavier than the other. This can be achieved, for example, by laminating a thin disk of lead with a thin disk of aluminum. This alters the coin center of gravity when it's stood on edge. This physical alteration has essentially no effect on the outcome of a flip if, for example, the coin is caught out of mid-air, which may be why this practice is so common. Well, that and the prospect of not wanting to have to search for it if it rolls under a couch or something. In fact, this sort of alteration has only really a negligible effect on the outcome of a flip, even if the coin is allowed to freely land on a surface, provided that the surface is giving or yielding, like a shag carpet or something. This alteration does affect the outcome, albeit slightly, if the coin is allowed to freely land and bounce around on a hard surface, and a little bit more so if the coin is spun on edge. Now, in our earlier video titled simply The Sample, this was perhaps to the surprise of some viewers, really not about samples or data sets at all, but really about extolling the critical importance of how a sample is realized. The revelatory process, we called it, the mechanism. Last piece of business here. In this mini-series, we relied on the standard normal or Gaussian distribution to model our sampling distribution. There's a very long tradition in this approach. One nice thing is that creating our critical region and calculating our p-values is very direct. We use the same distribution every time, a standard normal or Gaussian distribution. We can, in fact, perform our single proportion hypothesis test using an exact test, which makes use of the binomial distribution. And that's it. That's going to do it this time around. That closes out our mini-series. Thank you very much for tuning in. Don't forget to stay tuned for more QuantSlob.